Okay, so before calculating specific attributes, we'll first find out the first one of the important attributes of this line coding is power spectral density, with which probably 2 to 3 parameters can be extracted from that. Okay, so this goes with PSD of various line codes. Before getting into the individual specific line codes, it's always convenient to have a generic mathematical formulation, and depending on the line coding scheme, we can substitute those values and get the power spectrum immediately. Okay, so that's the basic idea behind it. So in general, we'll try to derive an expression for power spectral density, then we'll go with the specific cases. In this discussion, we consider a generic pulse as a told as g of t. Say this g of t is a generic pulse. It's nothing related to any rectangular pulse or return to zero or non-return to zero. So it's simply a generic pulse, okay, which represents binary 1 or binary 0, okay, which is actually the inverse Fourier transform of your g of f. Okay, this is what we are trying to find out what is the power spectrum of the output line coder. Okay, so we denote this line code symbol at any time instant. Say g of t is any shape of the pulse at any time instant, say as like this. Okay, this can take any shape in general. Okay, this g of t can take any shape. This is g of t. Okay, I'll just take a random pulse. Okay, this will go for a duration of say tb. Okay, this will have a duration of tb, some random amplitude to it. The transmitted symbol for binary bits of strings of ones and zeros, the transmitted waveform would look something like this. Okay, the transmitted waveform for any bit stream, say I'll call this as say s of t. The transmitted streams could be something like this. Say for binary 1, I'll choose this kind of waveform with certain random amplitude. Say for binary 0 or any other binary value, I'll take this shape. Okay, so it's kind of compressed version of the original binary signal. So the bit duration is same. Okay, so in general, I can say this is around k minus 1 tb time instant of time, and this is around k tb. So I can have any other shape as I wish. Okay, and so on. Okay, so this I can say this as k plus 1 times tb, and so on. Okay, this is my transmitted pulses, electrical pulses, depending on the binary data that I have. Okay, so in general, I can say that in general, what I mean is that if I have certain incoming bit stream, I can have outgoing electric pulses. Say for this, if this is incoming bit stream as x of t, if this is s of t, my line coder or baseband modulator, I can say that it will have an impulse response of say h of t, which is in fact what I have taken here as g of t. And hence, remember this word, this g of t is known as pulse shaping. Okay, so it tries to shape the pulse depending on the input that is fed to it, and hence it is a line coder or baseband modulator. Okay, unlike your any other modulation scheme, it generates electrical pulses in continuous domain depending on the input in binary format, and it tries to shape its pulse as per the scheme that is taken. So with yes.
So why can't we transform the digital waveform only?
Okay, digital waveform in the sense you mean to say binary forms, zeros and ones?
Yes, sir. Yes, sir.
Binary ones, say if I want to transmit with say binary ones and zeros, how do you want to transmit? Say if you want to say binary one on for certain duration and off for some other duration, how do you want to transmit by bits ones and zeros?
Sir, as we wrote using different line codes, polar and bipolar,
Correct.
using those waves, we are manipulating no, sir, like this.
Correct. Correct. Depending on that, we are going to manipulate. Definitely right. But this is a very generic scheme. I'm not talking about any line coding technique involved in this process, which I'm discussing right now.
Okay, sir. But during retrieval, based on the voltage, it will be mapped to 0 or 1.
Exactly. At the receiver, again, these are converted back to zeros and ones.
Yes,
Okay, so that's the basic idea. So please don't get confused. As Amrit was rightly pointed that I'm not talking about any specific line coding scheme at this point. So earlier discussion was listing down various types of line coding schemes, but as I listed few of the parameters which I need to calculate for all those line coding schemes, I want to find out say power spectral density for each of those line coding schemes. I just want to kill time. I just don't want to kill time for calculating power spectrum from individual types of line coding schemes, because I can have any kind of, as I told, the on duration could be 25% or 50% or 75% and so on. So I don't want to do for individual of such kind of line coding schemes. So I want to come up with a generic mathematical structure to find out power spectral density in general, and I'll substitute according to which line coding scheme that I'm talking about. Okay, so this discussion doesn't take anything which I've talked in the other half of this session. Okay, so please don't get confused. I'll definitely map this into all those line codings listed, but not right away. Okay, so with that, I'll try to cover this in a given amount of time. We'll see how far I can go with this. Anyway, so I can say a line code in general, okay, can be represented as okay S of t, which is your output, S of t, which is actually summation of all these pulses. As I have written the waveform there, it is just cumulative of all those pulses. Okay, say from n running from minus n to plus n, as capital N tends to infinity. Okay, so for infinite amount of duration, say it is running from minus infinity to plus infinity duration, it will have a random amplitude as a suffix n at nth instant of time, multiplied with the pulse shaped waveform, which is g of t minus ntb in general. Okay, so I'll map back to what I have written as waveform here. So an is a random amplitude. So if this is my s of t at this instant of time, this is some random amplitude which totally depends on the original information signal. This amplitude also depends on what kind of amplitude that is this x of t will have at k minus 1 times tb interval of time. Okay, and accordingly all these amplitudes are a kind of a uniformly distributed random process. So this an represents obviously is a amplitude of, so I'll write this specifically, this an is a random sequence. Okay, basically this is a statistical phenomena. All right, say and g of t in general is a low pass shaping signal. Low pass in the sense it is occupying only it will have amplitude only in the vicinity of t is equal to 0 or f is equal to 0 in frequency domain. Okay, so g of t is a low pass shaping signal. See, I'll not use that pulse here. It may lead to some doubts. So I'll just take as a low pass shaping signal, which is definitely a real signal. Okay, it's not any complex signal. All right. So with this mathematical formulation, I intend to derive per spectral density for any signal given and try to substitute all those specific line coding schemes in particular to that. This derivation will take at least 15 to probably 10 to 15 minutes of time since it's already 3:25. I don't want to do that. I want to stop it in between. I'll come back in the next session and continue this derivation from this part. Okay, so that will ease down the derivation for the next session. If you have any questions, you can ask, and then you can close this. I intended to complete this derivation, but it took a little time.
So what exactly is the g of t, sir, the function?
Yeah, g of t is this signal I have plotted here. G of t is simply a signal. I can say this is kind of an impulse response of a filter. Whatever signal that is fed to this, it has to get convoluted with this kind of a response and produce the output. So it h of t, as I've written here, it is nothing but g of t, which is kind of a filter. This is a modulator which takes the information signal and tries to convolute with this response and tries to give the output in form of continuous again in time domain. This x of t is basically, as I told, this is in a binary format. So this will give you ones, it's a streams of ones and zeros. Okay, so at one instant, say if it is binary bit 1, it has to pass through this pulse shaping or shape, simply some random shaping signal gets convoluted with that and gives some random waveform like this. For another bit instant of time, if bit binary 0 is coming incoming, so again it gets convoluted with the same signal g of t and gives some random pulse as a kind of this as for next bit of duration, and this process keeps keeps on continuing. Okay, so here I have not taken any specific amplitudes. It's not the plus p of t and minus p of t and minus p of t, as this is by bit 1, bit 0, and for bit 0 again I have taken the same duplication of the previous bit. It's not so. It's all these amplitudes are completely random depending on the random signal that I get at the input of this modulator. G of t is basically this kind of simple random signal which gets modulated with the incoming signal. Okay, okay, so that's about this part. We'll elaborate on this. It's kind of an interesting result that we'll be getting at the end of this discussion. So our job is to find out Fourier transform of this or frequency domain representation of this S of t, and hence if I take Fourier transform of S of t, okay, which I need to find out, which is S of f, okay, summation n minus n to n. So this is a discrete signal which is incoming to the this filter, okay, as n tends to infinity, because it could be an infinite discrete sequence. So that's understood. So if, that would be simply as I had written the Fourier transform of g of t, I would be representing as g of f, and the signal that I've got is simply a time shifted version of this g of t. That's g of t. That's a low pass shaping signal. So as we know from the properties of a Fourier transform, this is simply g of f times e power minus j omega ntv. Okay, using frequency time shifting property of your Fourier transform. Okay, so I'll pull out the independent terms. So g of f can be plugged out. So the remaining part is minus n to n an e power minus j omega n tb. Okay, so we need the power spectral density of the random signal s of t. Okay, so this is simply the Fourier transform, but we need to find out power spectral density of s of t. Okay, so that means that this is the Fourier transform. So if you take the density of this, that would give you power spectral density. So this is a spectrum of it. So if I take the density, that can be represented as s suffix s of f, which represents the spectral density, which is nothing but 1 over t. Okay, so this is the overall time period of the input sequence. So hence the density, in the sense it's normalized with respect to the time factor, which is nothing but magnitude of s of f whole square. This is actually is nothing but power is nothing but energy over time. Okay, so energy over time, that we know the relation, the basic relation. So the left hand side is now power. Okay, so s of f, the magnitude of s of f whole square is energy, kind of v square over time will give us the power. Okay, so for a random signal s of t being the random signal, which is the output, because input is a random process, output we also expect to be a random process. So for a random process, t can be tending to infinity. Okay, so for a random process s of t, okay, that is because input x of t is random. Okay, so for this we can take an infinite duration of the input. Okay, so therefore ss of f is simply as limit t tending to infinity, magnitude of s of f, sorry, 1 over t, magnitude of s of f the whole square. So just substituting the magnitude of that. Okay, so 1 over t, s of f that we have written earlier. Okay, s of f is this factor. So substituting from that, if I take magnitude of this, magnitude of g of f the whole square. Okay, and magnitude of this summation, as I have told, this an is a random sequence. That is, okay, if x of t is random, that implies this an is binary. As you know, these are the bits. It could be just ones and zeros. So each of these bits could be ones and zeros, and hence this an is a statistical, and of course with infinite period. Okay, and if I take magnitude of this whole square, since it's not a a definite quantity, it's just a random quantity. So we know that for statistical values, the magnitude of those values to the whole square is nothing but their mean values, as because they take all random values with respect to their amplitudes. So this is nothing but the mean, in the sense it is simply the mean square value of it. The square value, the magnitude of this whole square is nothing but mean square value of that, which is expectation of summation of n minus n to n an e power minus j omega n tb whole square. Okay, so this is the magnitude or the power spectral density we need to evaluate. Okay, and this can be simplified easily, as you can see that this part, okay, I'll take this part, Okay, this part, okay, if you carefully observe, this is of the form kind of magnitude, since exponential is a complex term here. Okay, although an is a real quantity, this e power minus j theta will raise to a complex quantity, and hence this is of the form uh, some complex quantity whole square. So this complete expectation, the inside term, it seems like this is some magnitude of a complex term, the whole square. So this, we know that from the basics of complex numbers, this can be taken as product of two complex conjugate numbers. Okay, so with that I can try to expand this into two terms, which I'll take as this way. Okay, so therefore this can be written as limit t tends to infinity 1 over t magnitude of g of f the whole square. Okay, so this expectation of this expectation of, so product of two complex numbers. So one I'll take with the timestamp as n, a small n, which is a n e power minus j omega ntv. So this is one term, as x plus jy is one term, into a conjugate of x plus jy, conjugate of the same quantity. So into another summation. So I will take another factor, which as another summation as am. The complex conjugate, the complex number of e power minus j theta is simply e power j plus j omega ntv. So this is not the suffix omega ntv. So this is plus j omega m times tv. Okay, so this gets split into two product of two summations. Simply this m and n are placeholders. Okay, so m and n are simply two different, which are identical to each other. Just for the sake of splitting of these two complex conjugates, I have taken two placeholders there. This can be simplified further as I can group few terms at this point whole square. This can be written as expectation, summation. Since expectation and summation are linear operators, so I'll take this summation, double summation, minus n, capital N, ranging from minus n to plus n. Okay, so expectation of product of two random values. So expectation of, okay, you can take this product of an and am. I can club these exponential quantities, which is nothing but exponential of j m minus n omega tb. Okay, so this is a simpler form of it, and you observe that this expectation of these two random quantities is nothing but autocorrelation. Okay, so note that this expectation of an times am is nothing but its expectation of two random numbers taken at two different instances of time, right? So this is the autocorrelation of your infinite period data sequence. Okay, so with that I can concisely write this representation of autocorrelation from your unit 1, that we have represented this autocorrelation function as simply r of k, where k is the time difference between two independent random quantities. So this is nothing but expectation of an. If I replace m with n plus k, if I replace this m with n plus k, where m is, that is nothing but the difference of timestamps between these two is k. right? So autocorrelation function is simply the function of the time difference between these two quantities. Okay. Also I see that t is tending to infinity. T is nothing but the entire duration of the data sequence. Okay, so where t is actually the entire duration of input sequence, okay, or the data sequence, which can be written as, okay, as you have seen, this is running from minus n to plus n. So there will be how many discrete values should be there here. So minus n to n, this will give you 2 times of n plus n is equal to 0. Okay, so there are actually 2 times n plus 1 quantities. Each of those bits occupy duration of bit as TB. So total duration of this data sequence is nothing but the number of data exists in the bit stream, which is 2n plus 1 times the bit period, where TB is bit duration, individual bit duration. Okay, so taking all these quantities and substituting back into our equation, this can further be simplified as, say, this power spectral density that we are calculating, remember. So this limit now, t is tending to infinity. Now I'll replace t with respect to individual bit duration and number of sequences in the number of bits in the complete data sequence. So as t tends to infinity, n is also n will also tend to infinity. So I can replace that concept of t tending to infinity. I'll pull this g of f the whole square outside. Okay, so which is independent of these quantities, which is nothing but limit n tends to infinity of, okay, so 1 over t, I'll replace this with 2n plus 1 times tb. Okay, and so there are two summations, two double summation. One is n, which is running from minus n to plus n. Okay, now m, as I know, I have replaced with n plus k. Okay, so m, if I replace with n plus k here, whenever m is equal to minus n, I just want to express in terms of k here. So this implies that, okay, so this implies that we make clear here. Okay, so therefore, so for m is equal to minus n, this implies k will be what? M is equal to minus n, k will be minus n minus n. And for m is equal to plus n, this variable k is capital N minus n. Okay, sorry, m is equal to plus n. Yeah, that's correct. So I can express this as, I mean, this is minus a negative sign. If I try to take out this, I can write this summation coming back to this quantity. This will vary from k, vary from minus n minus n to, okay, so whenever m is minus n, this is plus n. Whenever m is plus n, hope I'm right here, this is k is n minus n. That's correct, capital N minus n. Okay, so this is nothing but expectation of two random quantities which have got a difference of timestamps of k. So I can replace, I have already put this expression, so I'll replace this with simply r of k. That's the reason I'm taking out all dependency of m, the variable m here, and I'm writing in terms of k. So this r of k times exponential m minus n, the difference of those two times stamps is k itself. So this can be simplified as simply e power j k omega tb. Okay, So this will help me in several ways to write in a crisp form, and which will be helpful in finding out power spectral density of any given line code. Okay, so finally, okay, power spectral density is nothing but g of f the whole square. I'll take this tb, which is independent of n outside tb, and as limit n tends to infinity, 1 over 2n plus 1. Okay, as you can see, this k is equal to minus n minus n minus n, r of k e power j k omega tb. Okay, and this summation, I mean, any there is no quantity which is depending on small n here. Okay, I can interchange these summations. I can write this as n, varying from minus n to capital N. Okay, and there is no term for variation of this, so this is simply summation running up to 1. And as we know that summing of quantity just with a constant of 1 is nothing but this quantity is 2n plus 1. Okay, so this 2n plus 1 get cancels with this 2n plus 1, and this can be simplified further as power spectral density is nothing but g of f the whole square over tb. Okay, so as we know that we can omit this limit n tends to infinity, because we know that for random process is for infinite random process we can ignore that, and we can take inside this summation as n tends to infinity. We know that this k will run from minus infinity to plus infinity, r of k e power j k omega tb. Okay, so this is the required expression to calculate power spectral density of any given line code. Okay, so this is well known as discrete form of Weiner Khinchine theorem. We have studied this Weiner Khinchine theorem, where there was a relation between power spectrum density and autocorrelation function that we are expressed in probably in unit 1 as a pair of Weiner Khinchine quantities. But this is actually known as it's a discrete form of Weiner Khinchine theorem. Okay, so I'll try to list for the sake of clarity that where there are so many quantities involved here, I just list them down, where this autocorrelation function r of k, as you know that it's expectation of two random variables, okay, which is nothing but, as per the definition of expectation, this is nothing but an times an plus k times the probability of taken at the ith duration, say where I varies from 1 to l. Okay, so where l is in fact all possible values of the product an plus k. Okay, and pi is in fact the probability of the ith combination. Right, so g of f that we know, this quantity g of f is a spectrum of pulse shaping signal. Okay, so g of f is spectrum of pulse shaping signal which we have taken it as g of t. Okay. All right. So notice here that pi, which is the probability, it should be known. Otherwise, we will not be able to calculate this autocorrelation function and power spectral density. So note that this pi should be known. Should be known in prior. Okay, which is nothing but what do you mean by this pi is a probability, which is nothing but it's simply the PDF of the symbols. Okay, if it is simply a binary sequence which is ones and zeros, say for example, say if it is 1 and 0, it's simply the binary symbols that you are encoded and trying to shape into pulses. So this means, okay, the PDF is nothing but it's a discrete PDF. Remember, it's not a continuous probability distribution function. This is your discrete probability density function for equiprobable symbols ones and zeros. So this is nothing but, so if I say this has something like symbol this has V0 and V1 as two symbols, their distribution will be something like this, or density function can be plotted as, say if this has V1 and say V0. Okay, so if these are equiprobable, it's a uniform distribution of between these two. So as we know, for continuous uniform distribution, it's simply a rectangular pulse. Since it's a discrete, it will have values at the symbol values. Okay, so this means that this PDF probability density function of symbols to be known to in order to calculate in turn, which will give you the probability of the product of for the combinations of all the combinations of those two, and hence which will give us to which will help us to calculate the power spectrum of any line coding technique that is given to us. Yeah, one thing that we have already studied in your previous unit itself, where which is when you pass the signal as weakly stationary process, a random process through a filter, in particularly LTF filter, what its response. I just write that because that is also needed for the derivation. The power spectral density of a weakly stationary process. Okay, so you can check back your unit 1 where we have taken an LTF filter. Okay, an LTF filter. If the input say x of t, the input say this is x of t is a weakly stationary process. If it's a weakly wide sense stationary process, the output y of t, given that LTF filter has an impulse response of h of t, then we know that this is a known equation. I will not derive this because it's done already. We know that the relation between these two is nothing but expectation of y square of t, okay, mean square value of the output is related as minus infinity to infinity magnitude of h of f the whole square times the power spectral density of the input random process. Okay, this is nothing but s y of f. Okay, so this is already known by the characteristics of the LTF filter, where if its input is wide sense stationary, the output will also be wide sense stationary, irrespective of the nature of the impulse response. With these quantities, with these final two expressions, which is the calculation of power spectral density for any pulse that is given to us, using this and using the relation of the power spectral density of input and output of any LTF filter, we can apply these two expressions, the final expressions, to known line codes.